And together with Dennis Waterman and Stefanos Papavasiliou, we'll be doing this third. Hello everyone, welcome to our third session for the Accelerate Plaxis short course, the Introduction to Plaxis 2D. Thank you for attending here today. My name is Michel van der Sloot, and together with Dennis Waterman and Stefanos Papavasiliou, we'll be doing this third session on the parameters for sand, so how we can use parameters for sandy material and get it into Plaxis. Some notes and housekeeping up front. All the windows that you have on your screen are resizable and movable. Please check out the resource list. We noticed that the handouts were not available in the resource list, so we'll make sure that we get a link out there. I will put it in the chat after we started the session, so you can get it from the link there. If you have questions during this session, please use the Q&A box. Then we try to answer all your questions based on the response we got in the previous sessions, which was very good. We might not be able to answer all the questions here today, but then we try to follow up as soon as we can. If you're missing something on the media player, the lower button bar will activate or deactivate these windows. So if you miss something, please click on these items. If you don't hear us, or if you see things are not progressing, please use your refresh button in your browser or press F5 to refresh the connection. That usually solves the issue. If you want to download the certificate at the end of the session, you can find it from the last button at the bottom. Some other tips: make sure that you do not use any other bandwidth sensitive applications, otherwise the experience from our presentation might not be optimal. If you experience any issues during this session, please use F5 to refresh your browser, or just quick will be recorded. It will be available on demand after the session, so you can also rewatch parts later. So for today's session, Dennis will start off with the evaluation of the exercises, followed by introduction to the hardening soil model. Probably then we're halfway through our session for today. Then we do a quick break. I'll follow up with the determination of soil parameters for sand, and we'll give a quick overview of soil test, the special application that we have to simulate laboratory testing, and then we finalize with the homework assignment. So again, enjoy the session today, and thank you for being here. So Dennis. Seems Dennis is muted. Dennis will start with the introduction to the hardening soil model.
Can you mute me? Yes.
Yes.
Okay.
We can hear you.
Yes. Yep. So, okay. Thank you, Misha. I unmuted myself in the wrong place. Well, we will first talk a little bit about the homework assignment of last Wednesday. That was a rather simple one. Well, it was not so much work, but I do want to discuss a little bit some of the results that came out of there. So I will show you my screen now. And what you see on the screen is still the one, the presentation, the exercise as we gave you after the first session. So this is the excavation still using the Moore-Coulomb model. And what we did here is that we made 4 soil layers using the Moore-Coulomb model in all 4 of them. Now, In fact, this model has the same sand over the full depth. The reason that we use 4 layers here is that more Coulomb has constant stiffness, and we want to simulate the effect that with increasing depth, we actually have increasing stiffness of the sand. I mean, the deeper sand is more confined, it has a higher stress level, and therefore the stiffness is higher. And more Coulomb doesn't take that into account in a simple way. So we modeled it here as 4 layers. You can imagine if you would make more than 4 layers, thinner layers, and more of them, you get more accuracy if you do so. For this exercise, only 4 was used. The deepest layer is very stiff, so that is it's blue, but the top one is blue as well. So the lightest blue at the bottom. It's very stiff because we assume that there is very little going on, and Coulomb layers we asked you to do for today's homework assignment, to use it with the HS small model. And if you do it with the HS small model, then you will actually end up with this model here. And now you can see that the layering has disappeared. Why? Because the HS small model does take into account, first of all, that stiffnesses are not constant, but stiffnesses depend on the stress level. So initially, when we see just an increase of stress level with depth, it automatically results in an increase of stiffness with depth. How you exactly put that in, we will see immediately after the presentation, after this homework presentation in the first presentation. And also the HS small model has the possibility to take into account that soil behaves even extra stiff, you could say, in case strain levels are being very small. So this was the homework assignment. We will go to the results in a short bit. Now, I said that if you would really feel comfortable with it, you could even use the hardening soil model with it. And I will also show you that model. But let's first have a look at the soil parameters that we had to use for the HS small model. So I will open the material set here. And then the most important is that I open the parameters. Now we see here that we have a couple of stiffness parameters here. We have an E50, an E odometer, an EUR. So this is the first 2 are primary loading stiffnesses. One for shearing, well, for deviatoric loading. The second one for compression. The third one is an unloading reloading stiffness. And then if you go all the way down below the block of strength, we have a fourth stiffness, and that is called the small strain stiffness. So this is this enhanced, increased stiffness in case strain levels are very small. Now, those last 2, those small strain stiffness part, is not available in the hardening soil model. Now, we see here that it's set to 100 megapascal. G0 ref is 100 megapascal. If we would do this exercise with hardening soil instead of HS small, we have to think about this 100 megapascal because we're going to need it. So I will close the windows again, and I will now change to the hardening soil version of this model. So that will look something like this. So what you see here is that the first 3 layers of the more Coulomb model that just have an increase of stiffness with depth simply because the stress levels increase is now modeled with the hardening soil model. But the hardening soil model does not have this facility to make an extra stiff layer because the strain levels are so small. So that I had to introduce myself, which is the green layer at the bottom. So if you look at the parameters for the sand, now, those first parameters are exactly the same as we had for HS small. So we had the E50, the E odometer, the EUR, 2020 and 80 megapascal. They're exactly the same. But you can see that below the block strength, there is no small strain block. There is no G0 here. That 100 megapascal G0 is just not included in this model. This is the difference between hardening soil and HS small. Hardening soil cannot take into account increased stiffness with very small strain level. So what I did is that I made a second material set, which I just called deep sand here. And if you look at the deep sand material set, so what I did here is that I said, well, in the HS small model, this had a G naught of 100 megapascal. I want to make the layer very stiff. This is an excavation problem, so I'm going to unload the soil. So the stiffness that has to be very big is the unloading, reloading stiffness, which is the EUR, the third one in this list. And I translated this 100 megapascal small strain stiffness into an EUR. The small strain stiffness was G naught. And so for the EUR, I want to put in like an E naught, an E0. Well, we know that E0 is 2 times G naught times 1 plus the Poisson's ratio. The Poisson's ratio was 0.2. So 2 times 1 plus 0.2 is 2.4. So E naught is 2.4 times G naught. So that is how I came to 240 megapascal. 2.4 times the 100 megapascal. So the deep sand layer just has the small strain stiffness that in the HS small model I can put in one and the same material set, and in hardening soil I can't. So then you end up with the different models. So this is the hardening soil model. This is the HS small model, and this is the version with more Coulomb. Now, of course, you can wonder, okay, this is all very nice, but what does this exactly give me? Why do I have 3 different models, and why do I care I have 3 different models? Well, let's look at 2 specific results from both calculations and simply compare them. The first I want to compare is what happens with the soil directly behind my wall. So not in the excavation itself, but directly behind my wall on the same side where the anchors are. And just to see how the soil exactly behaves there, I'm going to draw a horizontal cross-section from the wall just below the soil surface until the right. So I use this button here for a line cross-section, and I just draw a line cross-section. I mean, it doesn't have to be super accurate. It's just below the soil surface that I'm drawing it here, and then I get my first cross section. I want to see vertical displacements in this one. Let me get rid of my command box here. So I will do the same for the other 2. So I will do it for the hardening soil model. I will also draw the cross section here, get rid of my command box, make sure that we will see the vertical displacement, and I will now also do this for the HS small model. So I will also draw here a cross section just below the surface. I will plot the vertical displacement, get rid of this here. I could even go a little bit further and say, well, let's get rid of the whole model. I only want to see the cross-section. If you do that, you press F8. There is a menu option for it, but F8 is the shortcut. If you do F8, you only see this one. So if you go to the cross-section, now you see the cross-section relative to the whole model. If you're not interested in the model, you only want to see the cross-section. With F8, you remove the model contour, which is what I have been doing here. And I do the same for this one. Now I want to see the next to each other, tile horizontally. I could even decide to get rid of the titles if I really want to. Okay, so here we have above each other, we have the settlements behind the wall for the 3 different models. On top we have more Coulomb, in the middle we have hardening soil, and at the bottom we have HS small. Now, what is the first that we see is that if you look at more Coulomb said the soil will go up. Now, that would be very strange because I didn't show you in detail this time, but I did it after at the beginning of the previous session. Mot-Coulomb does predict that the wall moves inward, which is what we expect. So it moves slightly into the excavation. And then, of course, behind the wall, space, new extra space forms, the soil fills up that space, and therefore you would expect the soil to settle. Nevertheless, Mot-Coulomb says that the soil doesn't settle, the soil goes up. So that is the blue graph, is that soil moving upwards. This is a typical result of Mot-Coulomb in excavation. Mot-Coulomb is a pure elastic model, and in this case, we excavate, so we unload the soil next to the wall, because we reduce the horizontal stresses, we unload it, and we just get a swelling. Because we get an elastic swelling because of the stress level decreasing, and because of the elastic swelling, the volume increases, and the volume increases a lot more than that little bit that the wall moves. So the soil moves up in Mot-Coulomb, which is not what we see in practice. So Mot-Coulomb is really not doing so well here. Then we see the hardening soil model. In the hardening soil model, we have a settlement behind the wall. That is exactly what we expect to see. And what we can also see is that the settlement, of course, is the highest directly behind the wall. If you look at the ruler on the horizontal axis, so the left side, which is at a distance of 15 meters, that is the position of our wall. And so 0 is the middle of the excavation, 15 is where the wall is. So at 15, we have the highest settlement. Now, that is good, we have a settlement. What we do know from practice is that if we go away from the wall to a distance of 2 to 3 times the depth of the excavation, that settlements are reduced to pretty much 0. Now, the depth of the excavation is also 15 meters. So if we should be 30 to 45 meters away from the excavation, we should see no settlements. Now, we start at 15 meters, so 30 to 45 meters is an x-coordinate of 45 to 60 meters. So if you go on that axis to 45 to 50 meters, then at 45 we see that the settlements are still like 1/3 of the maximum. And if you go to 60 meters a bit further, it's still like 1/4 of the maximum. So the amount of settlements at distances further away from the excavation in the hardening soil model are a bit overestimated. Because if you make a 15-meter deep excavation and you're 45 meters away from the excavation, really nothing is going to happen in your soil. You're outside your active shear zone and everything, and not really much is going to happen. Now, if you look at the HS small model, that is the lowest one. There we see that close to the wall, the settlements are very comparable to what we get from the hardening soil model. So that is very good. So hardening soil and HS small in that respect are very similar. But now we do see that if you go further away from the wall, and we are at an x-coordinate of 45, then which is 2 times the depth of the excavation, we indeed see that settlements have reduced to like 0, and at 60 meters there really are 0. So in the hardening soil model, the settlements close to the wall are good, but a bit further away they're overestimated. And in the HS small model, the settlements close to the excavation are good, and further away they're almost or really 0, which is also what we can measure in practice. So looking at settlements, we could see Mot-Coulomb is really wrong, because it says that the soil goes up and it should really go down. Hardening soil is good, and HS small is even an improvement on that, and mostly for the settlements further away from the excavation. How this exactly works, you will learn in the other presentations today. So the exercise of the homework for today was more like a sneak preview to what we will talk about during the day. So these are settlements at ground level. Let me close those again. So here I have my models again. Now let's also, as a second result, have a brief look to bending moments that occur in the wall. So I will, just for all 3 models now, plot the bending moments. I agree, I could have prepared this, but I also wanted to show you how to do this. I could select with the mouse the whole wall, some people prefer that. I usually just draw an area, and then whatever is in the area, Plaxis will tell me. Here it says, well, you just drawn an area, but inside that area there is a plate and there is an interface. What do you want? So I do the plate. Then I don't do select, because if I do select, you see it will only select it. But I actually want to view it. So if this, let me unselect it again. So if I draw the area and I say I want a plate, then I choose the view button. And if I choose the view button here, then it will immediately open the window to view it. So that is this one. I will do the same.
It seems your audio has been disconnected. Issues here?
Yeah, you can hear me now?
Yes, I can hear you clearly. Yes, yeah, thanks.
Well, okay, yeah, sorry, my volume changer actually fell on the ground exactly on the on-off button. I mean, how big is the chance that that works out? So, okay, my apologies. I was not aware of it. So what I did is that I now, I mean, after presenting the settlements behind the wall, I hope that was still audible for everybody. I now actually show for all three models the bending moments that occur in the wall for all three models. Well, maybe I should sort it in a slightly more practical way, like this, so that we do the order of the models. So now what we see here is the bending moments. We also see that the scales are different. So let me fix that first, because if you look at the scale, then you see that on the first picture it goes to 2500, on the second to 5000, and on the third to 2500. I want to have them the same scale, so I click on the second one, and then we have a button here to change the scale here. So I will click this. It's now set to auto scale. I will change it to manual scale, and then of course I want to scale it up a factor of 2. So I will just do times 2. And if I do that, now you see that all three pictures have a scale bar going from 0 to 2500. So now the pictures are very comparable. Now, what is the interesting one is that we have 3 different bending moment lines. They look very much the same, but they are not. And if you look in the title bar to the values, and we look, for instance, at the field moment, so that is like the maximum value that is drawn here in red, then we see that the more Coulomb model gives me a maximum value of minus 355 kilonewton meter. With hardening soil, I get 508, and with HS small, I get 470. So this is quite significant. If you look at more Coulomb of 355, and then I look at the hardening soil model, the hardening soil model is 150 more. I mean, 150 more is like 55% higher. The HS small model is something in the order of 120 more, which is like 35%. This is also very typical. More Coulomb for excavation problems have the habit of underestimating bending moments in your wall. So that is something very important. So it's not only that the settlements are the wrong way around, it also underestimates the bending moments in the wall. Now we know that hardening soil model slightly overestimates them, and HS small is the closest one. But that still means that if you calculate your excavation with the Moore-Coulomb model and you use the bending moment for the design of your wall, you may underestimate up to 30% your bending moment of your wall. If you look at the maximum positive value, then what we see is that for the hardening soil model, the maximum is in the toe. For the other two, it's close to the top anchor. The differences are quite small, but then if you look at the values, Moore-Coulomb says 258, hardening soil 212, HS small 217. So the bending moment close to the top anchor is somewhat higher in Moore-Coulomb than compared to the other two models. But since the values are smaller than the field value, the field moment is the one that you will take into account for the design of your sheet pile wall or whatever you want to use. And then you have to be aware is that Moore-Coulomb has the habit of underestimating bending moments for excavation problems compared to more advanced models, which give more realistic soil behavior and therefore also more realistic results. So that is about the bending moment. That was a second result I wanted to show. I also noticed that the previous time people said, okay, you showed me how to get forces out of my wall, but how do I get forces out of my anchors? And that is actually very straightforward. You can just click on the anchor. Don't use the arrow button. The arrow button is just very general select. The one underneath is to select structures. And with this one, I can just double click on an anchor. And if I double click on an anchor, it just opens a table. I mean, there is no graphic representation here because the anchor force is constant anyway. And then you can see that it says, well, in the table, the normal force, the actual force here is 345 kilonewton, and the minimum value and the maximum value, which is the minimum that occurred in the calculation until now. Well, the minimum was 0 because in the beginning the anchor was switched off, and the maximum is actually what we're having right now. And if you want to see them both at the same time, you could again, for instance, decide to select them both and view them in this matter. So now we see the anchor forces for both anchors. As I said, there is no graphical representation here for the simple reason is that it has a constant force. So yeah, drawing actual forces graphically would not be very exciting. So we just put them in a table. Now, this was pretty much what the homework assignment was about. So the amount of work for you was quite limited. Ascension Day and so on, and the weekend, we didn't want to make it too long. But you do see that if you change to another soil model, you get quite different results. And then you also have to start realizing what soil models are suitable for what I'm going to do in my project, and what soil models may not be very suitable at all. So this is very briefly about the exercise, and then we should now start moving into the presentation itself. And so we have been talking about hardening soil model and the HS small model, and then of course now I want to give some information on how those models in principle work. So this is what the next presentation is about. It will be an introduction to the hardening soil model. We will later also talk briefly about what is then new and extra in the HS small model. But the models are for like 80–90% similar. The HS small model is an extension of the hardening soil model. Now, if we first compare the hardening soil model with the Moore-Coulomb model, and we just look at soil behavior, then what what kind of features does the Moore-Coulomb model have? Well, the Moore-Coulomb model has linear elastic behavior until we reach failure. So there is some kind of failure criterion, which is shear-based. We have some kind of failure criterion, but unless we really reach that failure criterion, behavior of the Moore-Coulomb model is perfectly linear elastic. Whether I shear the soil or compress the soil, it's all linear elastic. If I shear the soil, then I may create plastic shear strains, but I can only create plastic shear strains when I am at failure. So if I mobilize 99.9% of my strength, the Moore-Coulomb model is still elastic. Only if I really reach failure, then suddenly I create plastic shear strains. And if I have the latency in my soil, then only at that moment I can also create plastic volume strains. So the latency can only occur at failure. If I'm almost at failure, the soil just elastically compacts or has no deformation. The latency can only occur at failure. Now, the Moore-Coulomb model has one stiffness parameter, which is the Young's modulus, and that one stiffness parameter has to be used for all possible soil behavior, which also means you may have to choose what exactly you want to put into the Young's modulus. I just explained we did an excavation exercise. If I do this with Moore-Coulomb, what do I put in my Young's modulus in the Moore-Coulomb model? And not a primary loading stiffness, because I'm not primary loading in an excavation problem. If it would have been an embankment problem, I could have chosen to do a kind of a odometer stiffness, a one-dimensional compression stiffness in my Moore-Coulomb model as the Young's modulus, because that is more suitable for that kind of project. Now, if you look at the hardening soil, well, first of all, the hardening soil doesn't have linear elastic behavior. It has elastoplastic behavior. Even before we reach failure, we already have elastoplastic behavior. So we have plasticity, permanent deformations before we reach failure. Again, that will create plastic volume strains by itself. So if I compress the soil in the hardening soil model, because I have permanent deformations, I will have permanent volume loss by compressing the soil. If I shear the soil, I get permanent shear deformation, because also in shearing, the hardening soil model is elastoplastic before reaching failure. If I have the latency by shearing the soil, I may create plastic volume strains due to the latency. So this is different from the plastic volume strains due to compression. But this is because of the latency. And because I can create this plastic volume strains due to the latency at shearing, and shearing occurs already before reaching failure, that means that the latency already occurs before reaching failure. So where Moore-Coulomb says even up to 99.9% mobilized strength, there is no such thing as the latency, only at failure. The hardening soil model says no. The closer you get to failure, the more strength you mobilize, the more the latency you will already develop, and not just at failure itself. The hardening soil model has multiple stiffnesses. We already saw that from the material parameters that I show in the homework assignments. It has a primary loading stiffness, and it has an unloading reloading stiffness. And the primary loading is for shear or deviatoric loading, and one for compression. So we can really specify what is the stiffness of the soil if I try to compress it, if I try to shear it, both under primary loading, or when I do an unloading reloading on it. Those stiffnesses are not constant in the hardening soil model. They depend on the stress level. And we will see in a few slides how they depend on the stress level. And as I already said, the latency is mobilized before we actually reach failure. Now, this is very simple. I just simulated a triaxial test here, a drain triaxial test with the Moore-Coulomb model, which is the graph on the left, and with the hardening soil model, which is the graph on the right, just to see the difference. And on soil, this is, let's say, primary loading. It's normally consolidated soil. It's primary loading, but it's perfectly elastic. Therefore, we get a straight line up, well, diagonal line, but it's straight. until we reach the failure level, which is reached at the deviatoric stress Q of about 200. Then we have perfect plasticity. I cannot exceed this level, therefore my stress strain curve now goes horizontal. If I'm going to unload the soil by just reducing the loads, then I get the unloading reloading curve, but we can already see that the unloading reloading curve is parallel to the primary loading curve. Remember, the Moore-Coulomb model only has one stiffness parameter, the Young's modulus. Whether I load the soil for the first time or that I unload it or that I reload it, it's always the same stiffness. So therefore the lines are parallel. On the right side, we do the same for the hardening soil model. Well, first of all, the primary loading line is not a straight line. It's a curve because it's not elastic. It's elastoplastic. And I develop more and more plasticity if I get closer to failure. And therefore, because of the increased plasticity, it starts to behave less stiff under higher strain levels. If somewhere I do an unloading, then you see that the unloading reloading line is very steep because the stiffness for unloading and reloading is considerably higher than for primary loading. So the graph on the right is we do the same. We load until a certain level, we unload, we reload, and then we continue loading until failure. But the graph on the right already looks a lot more like the curve you would typically get from a triaxial test. The one on the left, if you get this out of the laboratory, I'm afraid that instead of the soil, they put in a sample of rubber or something in the equipment, because a real soil doesn't behave to what you see on the left and does more behave to what you see on the right. It can still be improved, but it already is a lot closer compared to what Moore-Coulomb says is the result of a triaxial test. I already mentioned stiffnesses depend on the stress level. How does it exactly work? Well, let's say we do 3 triaxial tests here, and for all 3 triaxial tests we determine a stiffness parameter that we refer to as E50. E50 is the stiffness over the first 50% until failure. How does it exactly work? Well, if we take the curve here with the highest failure level, so that is like almost 250 as deviatoric stress level. Now, on that curve, if you take half of 250, so 125, so you look on the curve for the point where the deviatoric stress level Q is 125, you take that point and then you draw a straight line from the origin through that point of deviatoric stress of 125, and that straight line represents the stiffness E50. So the 50 refers to 50% of the failure deviatoric stress. And I've done this here for 3 different triaxial tests. It's the same soil, I just used 3 different cell pressures. So a low cell pressure, a medium cell pressure, and a high cell pressure. I have determined the E50s for the 3 cases, and what we can see is that if the cell pressure is higher, the E50 also gets higher. So E50 depends on the stress level. Now, it doesn't only depend on sigma 3, it also depends on other stresses, but sigma 3 we know. So if we want to make a stress-dependent stiffness, it's practical for E50 to be dependent on sigma 3, because sigma 3 is the cell pressure in my equipment, and the cell pressure I know because I apply it. Other stresses in my soil, because of during the test, I may not know, or they change during the test. Yeah, it's not very practical to determine a stiffness based on a test, on the stress level in the test, if the stress level changes during the test. Because then to what stress level exactly does the stiffness belong? So we use the sigma 3, the cell pressure, to determine the E50, and we say, okay, E50 depends on the cell pressure, and the cell pressure is sigma 3 in this case. And as I said, it's purely to make it easy to link this stiffness to a test. We can do the same for an odometer test. In this case, I don't have to do 3 tests. I can just do 1. It's a slightly alternative presentation, so it's not on logarithmic scale. It's also now having strain on the horizontal axis and vertical stress on the vertical axis instead of the other way around. As I said, it's also a linear scale. But if I make this graph, then the blue line is my test result. And then I can, at different levels of vertical stress, I can determine a tangent line, and the tangent line represents the odometer stiffness for that specific stress level. Here we use sigma 1 for the stress dependency, for the same reason why we use sigma 3 from a triaxial test. We use sigma 1 here on odometer test because we know sigma 1. If we do an odometer test, we either apply sigma 1, or if you do a constant rate of strain test, you measure sigma 1 directly. Sigma 3 here, of course, is a bit harder to measure because that is, you have to measure the ring force and so on. So if we want to talk about compression stiffness changing with stress level, it's easier to make a change in a model with sigma 1. That does not mean that in practice it doesn't change with any other stiffnesses, but if you want to build in a dependency, sigma 1 is the most practical because sigma 1 we know in an odometer test. We don't have to guess it, we just know what it is. So odometer stiffness depending on vertical stress level, simply to be able to match it to a laboratory test. And then we have unloading, reloading stiffness. Now, the hardening soil model assumes that we were going to take the unloading, reloading stiffness from a triaxial test. In practice, you probably more often would take it from an odometer test than a triaxial test. Fortunately, the results are not that different from the two tests. But here we have a triaxial test result with an unloading, reloading branch, and then the steepness of the unloading, reloading branch is the EUR. And because it comes from a triaxial test, the hardening soil model also assumes that it will be taken from a triaxial test, and therefore will depend on the sigma 3. So EUR is taken stress dependent depending on sigma 3 because we assume that you take it from a triaxial test. If you take it from an odometer test, you need a minor calculation to change the value, and then you're fine again. But we will see that later when we talk about parameters. Talking about the latency. Again, comparison, mole Coulomb, hardening soil. On the left side is mole Coulomb. So we see two straight lines. So on the vertical axis, we have volume strain. On the horizontal axis, we have axial strain. So we start our test, our triaxial test, completely on the left. This is a drain triaxial test. We start completely on the left. Volume strain is still 0. Axial strain is still 0. We start the test and we start to compress, according to the mole Coulomb model, our soil. It's linear elastic, so therefore we see a straight line going down. The volume is reducing while the axial strain is increasing. Now, at some point we reach failure, and at the moment we reach failure, if there is a latency angle defined, we actually have the latency. Now, from the lowest point, we have two lines. It's a bit hard to see on this slide. We have a blue one going horizontal. That is in case I didn't specify any latency. So then I reach the minimum volume at failure, and from that moment on, I generate shear strains, but no volume strains anymore. I just have shear strains. So I see a horizontal blue line, which I'm sorry is very hard to see. The purplish, pink-purple line is in case I specified the latency. So I reach failure, which is the smallest volume strain. I immediately mobilize my full latency, and therefore my volume starts increasing again due to the latency. The latency angle is constant. It's constant value, it's the maximum value. So I get a straight line up, which is the purple line, which is the increase of volume. And you see that after a while, your volume is back to the original one. And at some point, the volume of your sample gets even bigger than the original volume. Now, if you compare this with the hardening soil model, here the blue and the purple line are better to see. Well, first of all, when we start the test, we don't have elastic behavior. We don't have a straight line, we have a curved line. The blue one just slowly curves to a minimum volume again, just like the mole Coulomb did. It's just not elastic. The purple one, what we see here, is that before we reach failure, you already see the purple line deviate from the blue line. So we didn't reach failure yet, but I already see an effect of the latency when strength is mobilized more and more. I also see that it's not completely a straight line. It curves in the beginning. So at the moment the purple line starts deviating from the blue line, I slowly mobilize more and more the latency until I is when we get closer to failure, which is a more realistic behavior. I mean, soils don't suddenly change generally. I mean, there's no way that the soil has no latency, and when I add a tiny bit of stress, it suddenly has full latency. It's usually a process that is slowly being mobilized. So, summing up, the stiffness moduli in the hardening soil model, we have E50. This is a secant modulus. It's an average value. Remember, it's the average over the first 50% of the failure deviatoric strain. It's a secant value, and it depends on sigma 1. We have the EUR, which is an elastic stiffness according to Hooke's law, and it depends on sigma 3 in the hardening soil model because we assume you will get it from a traxel test. The stiffness changes with stress level. There is a tiny influence also of cohesion and friction angle, but very small. More importantly, it has a certain power value in there that says whether the stiffness should change linear with stress level or non-linear, and I will explain about that. And we assume that the input values, we have to give some kind of reference stiffnesses, and that those reference stiffnesses are taken at a stress level of 100 stress units. That means that if you calculate your project in kilopascal, then if you fill in the stiffnesses, those are the stiffnesses at 100 kilopascal stress level. But if you do it in kilopounds per square foot, then the reference value will be at 100 kilopounds per square foot. So it's 100 stress units depending on what stress unit you use. Be aware that E50 and E odometer, although they're called something with E, they're not elasticity moduli, they're not elastic stiffness parameters, they are plastic stiffness parameters. They include elastoplastic behavior. EUR, on the other hand, is also called something with E, but that actually is an elastic stiffness parameters and really follows Hooke's law. So you could say it's kind of a Young's modulus, but then one that is stress dependent. E50 and E odometer are not. They're called E, but the E does not refer to elasticity here. They're plastic parameters in this case. Now, how does this look like? The formula. So E, whether this is E odometer, EUR, or E50, this is the stiffness that we actually have at any moment in our calculation. That depends on the reference stiffness, EREF, that we have to fill in as a user. And then we have the equation that has some cosines in it and cohesion. But most important, it has sigma and Pref. Now, Pref is that reference stress, that 100 stress units stress. And sigma is my... For an E50 or an EUR, this is sigma 3. For E odometer, this is sigma 1. Well, actually, internally, we use sigma 3 over K naught and C, but in an odometer test, sigma 3 over K naught and C is exactly the same as sigma 1. In a plane strain analysis, it's almost the same, but we still say that we depend on sigma 1. And then we have that power M. Two remarks here. In the equation, we see minus sigma plus Pref. That is because the reference stress is always filled in as a positive value. But in Plaxis, stress it's minus 100 because it's compression. So this plus minus is to come over this sign convention thing. And the second remark is that power of stress dependency, that M, which determines whether the relation between stress and stiffness is linear or not. If M is 1, the relation is linear. And for clays, this is a pretty good estimate. For clays, this M is indeed 0.9 to 1. For sands, it's more like 0.5, which means that the stiffness increases as a square root of the stress level. For silts is 0.5 to 0.7. If you have a sandy clay or a clayey sand, you end up somewhere between the 0.5 and 1.0, depending on how much sand is in there or how much clay. For certain sands, it could even be slightly smaller than 0.5, like 0.4. For rocks, quite often we just use 0, so no stress dependency. Because the change of stiffness due to the stress level is very, very small because of the high stiffness of the rock. Values larger than 1 we generally don't see, and 1 is also the maximum that you can fill in the hardening soil model. Now, E50 is a parameter we get from a traction test, which is very nice and practical because we can just measure it. Now, if we do this, since we get it from a test, we have to realize is that in the test, we probably have some elastic behavior, some plasticity due to shearing, and some plasticity due to compression behavior. And those we have to, if those are being considered in a drain triaxial test, this is what the graph is that you see below. What I did here, and of course in Plaxis being a computer software, I can do that. I mean, I cannot do in reality a triaxial test and say, well, in this triaxial test, I only want to measure the elastic behavior. I wouldn't know how to do that in the laboratory, but of course in Plaxis I can do so. And so what I did is that I said, well, let's see what is just the elastic part. I took my soil material parameters and I first over-consolidated the soil. So I compressed the soil a lot, then I unloaded it, then I sheared it a lot, then I can't really unshear it, but you know what I mean. I unloaded it in shearing. And then, yeah, my material has been over-consolidated in both compression and shearing. So then if I do a triaxial test, it will be pure reloading. And if it's pure reloading, I only get the elastic part of the soil model. And that is that very light blue turquoise line you see on the left. I hope it's easy to see because the color is quite light. So that line represents the elastic behavior. And you see that, yeah, I get a certain amount of strain, elastic strain here by doing so. Well, what I could also do is that I say, well, if I take my soil and I only shear it and then unload the shearing, but I don't do this for compression, and then I do my triaxial test, then under compression, my soil is still normally consolidated, but under shearing, it's elastic. And in that case, if I do my triaxial test, then I get elastic behavior and plasticity due to compression, but not due to shearing. And that is the red line. So the difference between the light blue line and the red line is plastic behavior due to compression, because in shearing, my soil still behaved elastically. And then the blue line that I finally get, the dark blue line, is just using the material normally consolidated in compression, in shearing, and this is like my normally consolidated triaxial test. So I see three lines, the first line just being elastic, the second line being elastic plus compression plasticity, and the third one is elastic plus compression plasticity plus shear plasticity. So if you look at the blue line and you look at where the arrows are given, so I have a total strain level of close to 2% here. Out of the 2%, like 60% is shear plasticity, and then about 20% is elasticity, and 20% is compression plasticity. So that means that although we assume that a triaxial test is a deviatoric loading test, and which is true, is that if you look at the strains that you get out of this test, those are not pure deviatoric strains. About 60% is deviatoric strains, and the other 40% is part plasticity due to compression, because in a triaxial test, I do compress the soil somewhat, and there is a part elasticity in there. Now, I can do something similar with an odometer test. And if I do this with an odometer test, I model the odometer test if the soil would behave only elastic. So I over-consolidate it under compression, I over-consolidate it under shear. Then I only over-consolidate it under compression, but it's normally consolidated under red line here. And then I just have it normally consolidated for both shearing and compression. That is the blue line here. Then again, I see that the green line represents elasticity. The difference between the green and the red line is plasticity due to shearing. So yes, in a odometer test, the soil is being shared as well. Not much, but it is being shared. It's not perfect one-dimensional compression. And then the difference between the red line and the dark blue line is my compression part. Now, the ratios differ a bit, but what we can see is that in this case, from the total settlement, the total vertical strain, I measure something like 40% is compression plasticity, 40% is elasticity, and 20%, well, less than 20% is due to shearing. Those ratios may change a bit depending especially on your elastic stiffness, but there is some shearing going on as well. So I have two tests, and in two tests, I get two test results that give me two different stiffness parameters, E50 and E odometer. But both the parameters are actually based on a little bit of shearing, a little bit of compression, and a little bit of elasticity. Now, that is, of course, all very nice, but it's not so handy to have this in a mathematical model, because in a mathematical model, I would prefer to have one parameter for elasticity, one for shear plasticity, and one for compression plasticity. But I cannot really determine that, because I cannot really in the laboratory say, well, I do a triaxial test, but I only want to see shear plasticity. I mean, you can tell the soil, but I don't think the soil will react any way different than it normally would do. So although E50 and E odometer are very easy to determine, they are elastoplastic parameters that includes three different effects of the soil: shear plasticity, compression plasticity, elasticity. It's not so practical for a mathematical model. And therefore, the hardening soil model internally uses different parameters than the one we put in. Internally, it really uses parameters that represent elasticity, shear plasticity, and compression plasticity. But of course, those parameters I cannot get as a user from a laboratory test. So it has to do with conversion. So as a user, I specify E50, E odometer, EUR, and then internally, it will actually generate parameters that it uses for the model. Now, why is this important for you as a user to know? For several reasons, but the main one is that, first of all, there is no equation, no analytical solution to get the internal parameters from the E50, E odometer, and EUR. So internally, it has to do a little simulation. And it does so. So at the moment you fill in the parameters, you press the OK button. What the hardening soil model does is that it actually simulates a triaxial test and an odometer test. It makes a first estimate of the internal parameters, just whatever, set them all to 1 or something. A triaxial test and an odometer test, it does determine from the triaxial test and internal and odometer test the E50 and E odometer. It compares it with the values that I as a user put in. And if they don't match the user input, it adjusts the internal parameters, does the simulation again. And in this way, it iterates to internal parameters that after doing those two tests, represent the E50 and the odometer that the user put in. So that sounds like a lot of work, but you don't even notice. If you fill in the parameters, you press OK, you don't even realize that in the background there's a very fast little iterative procedure to determine the internal parameters. It needs 3-4 iterations and it found them. Again, why is this important? Because since this is a small procedure, it may not be able to find internal parameters. The conversion has a couple of limits. And one of the limits is on the ratios between E50, E odometer, and EUR. We cannot use very extreme ratios between those parameters. So, for instance, if EUR becomes more than 20 times E odometer, it can usually not determine the internal parameter for compression stiffness anymore. And Plaxis will give you a message, and the message will be something like EUR too high or E odometer too low, and it gives you the value of the EUR that you can still use, like the most extreme value that it can still accept. The same counts for the relation E50 over E odometer. If that relation gets higher than 2, then it quite often doesn't accept it anymore. What does 2 mean? E50 over odometer being higher than 2 usually means it's a very, very soft soil. The same counts if EUR over E odometer is higher than 20, it's a very, very soft soil. So for those very soft soils, you may not be able to use the hardening soil model. Thankfully, we have plenty of other models in Plaxis. You could use the soft soil model. If your soil is really that soft, it may actually also have creep behavior. So you have the soft soil creep model, for instance, that you could use. But the hardening soil model may be impossible to use. If all three stiffnesses are equally important, you really have to have those values, and then hardening soil will tell you. So it's not that it will sneakily calculate with different values than you put in. If it has a problem because of the ratios, it will tell you, and if it tells you, you can act accordingly. Now, what's stiffness? Well, we have the stiffness model, which is important for what behavior. Now, let's look at an excavation in general, like the exercise we did. So then we excavated, we may have anchors. Now, underneath the excavation bottom, we have a lot of unloading. So EUR is very important. If the unloading is quite extreme, then it could be that the vertical stresses get so low that we also even get some deviatoric behavior in. We have a reduction of the horizontal stresses and not from the vertical stresses. So there, again, we have some unloading. But if the horizontal stresses are reducing and the vertical stresses are not, then sigma 1 minus sigma 3, which is approximately vertical stress minus horizontal stress, sigma 1 minus sigma 3 is going to increase. So I'm going to have more deviatoric stress in my soil, and we know that deviatoric stress is linked to E50, or E50 is linked to deviatoric stress. So next to the wall, E50 is a very important parameter. The soil behaves there mainly according to the value of E50. Underneath the excavation bottom, it's first EUR, unless at some point the vertical stress gets so small that the difference between vertical and horizontal stress becomes very large again, then it's more like E50. Then also you have deviatoric effects in there. You don't have to think about that yourself. The model will take that into account for you. If you are at very large distance, then strain levels are very small, and probably the soil will behave stiffer because of those very small strain levels. So then we have an E0 or small strain stiffness, initial stiffness, whatever you would like to call it. Now, if I would model this with the Moore-Coulomb model, I would actually have to make a material set underneath my excavation bottom with a Young's modulus representing my unloading, reloading stiffness. Next to my wall, I have to use a different material set representing, well, a mix of unloading, reloading, and deviatoric loading. So I have to use a Young's modulus according to that. I probably have to make a couple of material sets because if my wall is quite long, I also have to take into account as with depth, I may want to take an increased stiffness. And then further away, you have to define another material set in Moore-Coulomb with an E0 to take into account a very high stiffness because of the low strain levels. The hardening soil model takes this into account for you automatically. It just keeps track of how the stresses changes, and then it uses the correct stiffness accordingly. So you don't have to think about it. The model will do this for you. With Moore-Coulomb, you have to think about it. And if you put below your excavation bottom a value of EUR, then it could be that if you excavate further and further, the vertical stresses reduce a lot. Horizontal stresses at larger depth are a bit bigger. Therefore, the ratio between horizontal and vertical stresses gets quite large. I get deviatoric behavior that during the calculation, I have to change my Moore-Coulomb material set because I have to change my Young's modulus, because my Young's modulus is not just, at some point, not just pure unloading anymore. It's now unloading with deviatoric loading. So I may have to change that as well. Again, in hardening soil model, this happens automatically during the calculation. Now, in an embankment problem, let's say it's on normally consolidated soil, EUR is of minor importance. The E odometer and the E50 are the most important ones. If it's a wide embankment, In the middle of the embankment, the soil is mostly one-dimensional compressed. So E odometer is the most important stiffness parameter there. If you get closer to the toes, then of course you see more deviatoric loading, because the embankment pushes the subsoil down, and the subsoil will actually go in either direction horizontally away. And because close to the soil surface, the horizontal movement is quite big. At deeper depth, the horizontal movement is quite small. Therefore, you have a deviatoric effect. So closer to the toes of the embankment, E50 is the most important stiffness parameter. In the middle, E odometer is. And again, in more coulombs, you would have to define different material sets, and then you have to choose, where does E odometer stop and E50 start, because I have to change the Young's modulus, or maybe you want to make several vertical zones with different values. Hardening soil model will take this into account for you. You specify the E odometer, you specify the E50, and the model, according to the changes of stresses, will know what to do internally. One thing we didn't touch, because the examples I gave is undrained behavior. And the hardening soil model is a model that is completely defined in effective stresses. Stress-dependent stiffness is depending on effective stresses. So the stiffness changes if the effective stresses changes, not if the total stresses changes. So we cannot use the hardening soil model in a total stress analysis, because the pore pressures don't change the stiffness of the soil. You could say, yeah, but undrained soil behaves considerably stiffer than drained soil. That is true, but that is not because of the soil. That is because of the water. It's the water that makes the soil behave so stiff, not the soil itself. Hardening soil model describes how the soil stiffness of just the soil particles change when stresses change. So we need effective stresses for that. Also, if you look at the equation of the stress-dependent stiffness, you know that there is cohesion and friction angle in there. So in principle, to use the hardening soil model, you also would have to use effective strength parameters, friction angle, and cohesion. You could decide to use the hardening soil model with an undrained shear strength. So then you put the friction angle to 0 and you fill in the undrained shear strength. But you have to realize is that if you do so, the stiffnesses become constant again. If you look at the equations a couple of slides back and you fill in phi is 0, then you will see that the whole middle part of the equation falls out, and it will just say E equals to E ref. Well, times, what is it, 1 to the power m. But yeah, 1 to the power m is always 1, whatever m is. So that means that E equals to E reference. So with undrained shear strengths in the hardening soil model, you lose stress-dependent stiffness. Stiffness is constant. Now, also the principle of compression hardening, that if you do a compression of the soil, that you generate permanent volume loss because of plasticity, is also lost if you fill in a friction angle of 0. So you can use the hardening soil model in an undrained analysis with undrained shear strengths, but it's not really the full hardening soil model anymore. Stiffness-wise, it's basically behaving like more Coulomb. Okay, you still have shear hardening, but you don't have compression hardening anymore. So it's a very limited version of the hardening soil model. So Plaxis mentions it in like an information box. It doesn't give you a warning on it, but you should be aware that to really fully use all the functionality of the hardening soil model, you should use it in effective stresses with a friction angle and a cohesion, and not with undrained shear strengths, although the latter is allowed to do. So when do you use the hardening soil model? Well, the hardening soil model and the more Coulomb model do have the same failure criterion. So you could say, well, okay, then if I'm only interested in failure, it doesn't matter. Not entirely. If you're only interested in drained failure, then indeed the hardening soil model and the more Coulomb model behave pretty much the same. It will give you the same factor of safety and things like that. But because the hardening soil model being an elastoplastic model and it already having plasticity before reaching failure, you do see that in undrained behavior, the two models behave differently. We will mostly talk about this on the Wednesday session. On the Wednesday session, when we talk about clay, I will also say a little bit about undrained behavior, and then we will also see how hardening soil in undrained behavior is different compared to the more Coulomb model. So if you want to know about that, you will have to come back on Wednesday. As I said, hardening soil model is elastoplastic. It gives a better prediction of displacement we could already see that from the excavation exercise, where Moore Coulomb says that behind the wall, my soil goes up. I mean, my wall moves inwards, but still my soil behaves goes up, while it shouldn't be. I should get settlements there. So the prediction of settlements of hardening soil is better than Moore Coulomb, especially when we have a lot of shearing and when we have unloading, reloading. So typically for tunnel projects, for excavation projects, Moore Coulomb can give seriously wrong results, and hardening soil model doesn't. So for those kind of projects, we highly recommend using the hardening soil model and not the Moore Coulomb model. Of course, you could say, yeah, this is all very nice, but then I need an E50 and an odometer and an EUR. How do I get those? Now, if you would have said this to us 15, 20 years ago, I would completely agree, because there was not so much experience with the hardening soil model. So then you really would have to do the triaxial test, the odometer test. And we all know that for especially smaller projects, we usually don't do those laboratory tests, only when we have very big projects, and then you probably still even have to fight to get them. Nowadays, of course, it's a bit easier, because there is a lot of literature, there are publications, there are books, a lot of correlations. So, okay, hardening soil parameters can be correlated to things to a certain degree, to CPT, to pressure meter tests, dilatometer tests. Be aware that if you correlate them to in situ test, there is no such thing as one equation. I mean, the link between the parameters and a triaxial test is there. It's established. It's always the same. To an in situ test, it is not. So you probably need local correlations. If you look in literature and you find a correlation between a cone penetration test and hardening soil model done for clays in Northern Europe, and you're not in Northern Europe because you're in Southeast Asia, those relations are probably not valid for you. Be very aware of that. So you really need local correlations, which is different from relations with laboratory tests, which are more general. But it can be done. So therefore, you can do a good estimation based on limited data or in situ test nowadays, simply because the experience is there. It's just a matter of finding it. Also, be aware that even if you have estimated data, you generally still get better results than when you would use the Moore Coulomb model. Of course, I assume that your estimated data makes some sense. I mean, that sounds obvious, but you would be surprised that sometimes we get questions from people say, well, I did some laboratory tests and I did some field tests, I calibrated them, and yeah, the best result is reached when cohesion is negative, but I can't put it in the model. Well, of course not. I mean, we don't allow negative cohesion in the model. I'm not sure how that physically would look like. I mean, the sand particles or the soil particles reject each other and want to move away from each other. What is negative cohesion? So estimated data gives better results than the Moore Coulomb model. Estimated data, of course, within the limits that you could expect. If you put in the hardening soil model for a soft clay a stiffness that feels more like a rock, then you will not get better results. But within reasonable limits, that is the case. So even if you don't have all the tests into great detail, using the hardening soil model may already give you an advantage. It may not give you the full advantage of the best results, but it will already be better than the Moore Coulomb model. Now, the final slide here. This is the choice of model in Plaxis to get the best settlements and deformation prediction. I already mentioned something about our strength, and we will talk about it a bit later on Wednesday. So depending on the kind of loading, is it a primary loading, like for instance for a dam or an embankment? Can also be a foundation plate on normally consolidated soils. Is it unloading with deviatoric loading? Excavations, tunnels. Is it pure deviatoric loading? That could be still things like foundations on over-consolidated soil, especially under horizontal loading. That may be more pure deviatoric if you have to take into account strong wind forces or something on your foundation. And then secondary compression, creep. Then it depends on the soft soil, on the kind of soil. Is it a very soft soil, a normally consolidated clay, a soft normally consolidated clay, a peat maybe? Is it a hard soil, an over-consolidated clay? You can think about things like a London clay or Boston blue clay or something like that. In the soft soils, you're more thinking about well, a lot of the clays here in Western Europe, but also things like Bangkok clay, and those are very soft. Singapore marine clay is also a very soft soil. The hard soils are then the over-consolidated ones, sand and gravel. And then you see the different models. So there can be soft soil, soft soil creep, hardening soil, H is small. More Coulomb is not really in this list. More Coulomb does not give you the best settlement and deformation prediction. If you're really into having a good settlement prediction, a good deformation prediction, more Coulomb is generally not the way to go. I mean, you can always, if you have measurement data, play around with the stiffness parameters in different more Coulomb sets and match measurement data as like a back calculation. But as a prediction, it's very, very hard to do. And I wouldn't say impossible, but it's very, very hard to do. For a good prediction, you need a more advanced model. And we have several for different kinds of material that you can use in this case. Now, this was my brief introduction to the hardening soil model. Misha will take over to talk more about the parameters, because now we just briefly mentioned what they mean, but you also have to somehow get them and calculate them, and he will talk a little bit more on that. I'm not just looking at Misha whether we first have the break planned, or that he first wants to continue with the soil parameters.